And welcome to SanfordFlipMath. This is AP Calculus. We are working through the AP Calculus course mainly through the Finney, Demana, Waits, Kennedy Calculus book. We're at the spot in the course where we have done what we would consider the first half of the course, derivatives. Obviously, derivatives will continue to play a role as we continue in the next half of the course, but this second half of the course is the integral calculus part of the course, and we'll talk more about what that actually means as things come up. The main focus in the first half, the derivative or differential calculus, is on slopes and slopes of things that are changing, and then how those mean things and how to use them. Whereas now we're going to look at integrals, and we'll start looking at integrals by talking really just about the relationship between a velocity and time situation and area on a graph. And we'll start that by, so we're in section 5.1 again of our book. Well, we'll start that with just a basic idea, and we go to this kind of idea. If I'm traveling at 60 miles an hour, and if I'm able to keep that at a constant rate for, let's say, 2 hours, then the idea here is that I've traveled, well, 60 miles per hour times 2 hours, so 120 miles. And if we were going to look at that on a graph, where this is time and this is the velocity, okay, so here I have my velocity of 60. And I drive along and I go to 1, 2, 3, let's say 2 hours. Okay. Well, if I take then 2 times 60, here's this 120. This 120 miles is actually the area on this graph. Now, please understand that miles is obviously not an area. That's a linear measure. You measure with a tape measure, you measure with an odometer or something like that. But the idea here is that if I'm looking at a velocity graph versus time, then distance, okay, so I should probably write this, on a velocity versus time graph, distance, I dotted my A, sorry, is area. And really it's because it's that whole idea of distance equals rate times time. If we're talking about a rectangle, area equals length times width. So there's a connection there. Okay, don't spend your life on it, but the area between a velocity time graph and the x-axis. So if we look at that area between those two things, I'm just checking my wording there because I don't want you to get confused. The x-axis is in distance. So the area between the graph and the x-axis is distance. Okay? All right, so with that idea then, we need to have some techniques because, that's all well and good if we're talking about a constant velocity. But what if we're talking about a velocity that's increasing? Okay, so if that's true, then maybe we need to do, again, distance and area here are the same thing. So in this case, if I was looking at this kind of a shape, then I'd be talking about the area of a trapezoid. And now we got to remember, okay, how do you find the area of a trapezoid? Okay, well, when it really gets interesting, that's my euphemism for hard, is what if the velocity is constantly changing in a in some kind of a funky way? So again, if we're talking about velocity versus time, and we wanted to find out distance, again, we'd have to find area. And so we'd be looking at this area, and now the question is, how do you find that area? Well, a big chunk of what we're going to be doing for the rest of the course, or a lot of the course anyway, is exactly that. How do you find the area when things aren't cute? And much of what we're going to do is going to involve rectangles to approximate area. Oops, sorry, that was a biff. That should be up here. Okay, so that's actually where we're going to go, and we will start working on that relatively soon. Okay, so the idea is find the area of a bunch of rectangles, add it up, and go from there. All right. Well, let's start with one that's a couple that are fairly straightforward, kind of similar to what we just did. Okay, so if I have a car moving at 50 miles an hour for 3 hours, okay, so the velocity is 50. We're going to go for 3 hours. We want to find the distance. Okay, so remember, distance for us is going to be area if we're talking about a velocity curve. So in this case, it's like length times width, same idea as rate times time or time times rate. Okay, so I can just pick that up. Here's my speed, my velocity, and so the area in this case is just going to be 50 times 3, so 150 miles. Okay, and if you're being a unit person, that was miles per hour times hours. Those divide out, and you're with miles. So for all of my physics and chemistry people, there you go. Okay, a little more interesting. Velocity is 4t plus 1. So this is t, this is v. And what we want to know is what's the distance after 3 seconds. Okay, so we're going to start out at 0. All right, well, let's graph the 4t plus 1. Okay, so this has a, quote, y-intercept of 1. It's going up 4 and over 1. And I'm going to run out of screen, but you get the idea. Yeah, it's pretty close. And the idea is I'm going from 0 to 3. So I'm going to start here at 0, and I'm going to go to 3. And so what I want to know is, you know, we're making that transition to that we're talking about area if we're talking about distance. So I need to know this area. Now, this is not a triangle. It looks like a triangle. Okay, please understand it's really not a triangle. Because right here, there is a little side here. Okay, so I'm going to give you a couple options. Your goal now is, remember, distance is area. If we're talking about a velocity graph versus time, and we are. So one way to do this would be to just chop it up. That bottom piece is a rectangle. 3 times 1 is 3, right? Because the height here is 1. Okay, base times height. So that area is 3. And now this thing is a lovely little triangle. Okay, well, I know that this width down here, the base of this triangle, okay, so area of a triangle, 1/2 base times height. So 1/2 times 3 times, well, how high is this? Well, whatever this y value is, this height is 1 less than that. Okay, so maybe we can just put in 3. So 4 times 3 plus 1, that'd be 13. So this point is at 313. So the height of this triangle is 12. So 1/2 of 36 is 18 plus 3. So that area or distance is just going to be 3 plus 18 equals 21. And this, well, we weren't given units for velocity, so let's make some up. Let's say it was centimeters per second. Okay, so 21 centimeters. Okay, so that's the idea. Find the area. Well, yeah, suddenly that's not fun anymore. Again, velocity, time, let's say this is again centimeters per second for velocity. Well, I'm supposed to find now the distance for the first 3 seconds, and this isn't cute. So this is what I need to find. I need to find this area. Well, how are we going to do that? I mean, I don't have a formula for area of half a parabola. So what we're going to do is some approximating. Okay, so there are really 4 methods for approximating. This last one we're going to do at the end of the chapter, but right now we're going to focus on these three. Okay, and one of them is called LRAM, which is left rectangle approximation method. Okay, so the acronym is LRAM. Okay, and so as you might guess, there's right RAM and mid RAM. Okay, so just a quick note. So this is left, this is right, and this one is mid. Later, this one is actually trapezoid. We'll deal with that later again. Okay, so what a left rectangle approximation method means is we're going to divide this thing up into separate rectangles. Now, I'm going to use 3 rectangles right now just for ease of computation. Okay, so the problems you might get might say subintervals. Okay, so I have an interval from 0 to 3. And then we're going to use 3 subintervals. So what that means is I'm going to take this distance from 0 to 3 and I'm going to cut this into 3 chunks. And I'm going to make a rectangle out of each one. Okay, if it was trapezoidal rule, we would make a trapezoid out of each one. And what we're going to do is, since it's left RAM, what that means is go to the left side of the rectangle, go all the way to its Y value, and we're going to make a rectangle there. Okay, so that's a left endpoint of the interval rectangle. Okay, so this is a rectangle. Now, I need to make another one. So I'm going to go to the left side of that one. Okay, I don't know exactly where it is. And I'll do that. And then I'm going to go to the left side of this last interval, and I'm going to stop right there because that's where its Y value is. Okay, so this is a left corner. The left corner is on the parabola. Okay, and that's true for all 3 of these. The left corner of each rectangle is on the parabola. Now, probably worth noting that when we get done finding this area, it's not going to be right. It's going to be an approximation. Okay, and the reason is, as you can probably tell from our little picture here, there's some stuff sticking out. So all of that stuff is error. We are going to overestimate the distance in the area this time, and that's because of the way the curve happens to be going. Okay, so just a quick little note here. Because it was decreasing there, the left RAM is an overestimate. If I had something like this, and we'll see this in a second, then a left RAM would actually be an underestimate because I'd have error that I wasn't counting. So instead of overcounting, I'd be undercounting. Okay, so quick little note to self here. For LRAM, if the function's increasing, it's an underestimate. And if the function's decreasing, it's an overestimate. Now, what I think you should do with that, I mean, and this will be an issue, and yes, you do need to know that. I think it takes 2 seconds to sketch something like I just did, and you know, instead of memorizing it, just kind of picture it. Okay. All right. So this is really not the problem we're working on right now, but you need to be aware of it. So if you didn't catch that idea, then back it up and rewrite it and write it down. Okay. All right. So we're going to actually do this calculation. Okay. So our area is going to be based on these 3 subintervals. And what we're going to do is find the length times width for every one of these rectangles. Okay, so this rectangle has a width of 1, or a base of 1. So does this one, so does this one. So I know I'm going to be doing 1 times a Y value. I'm going to have 1 times another Y value. And I'm going to have 1 times another Y value. Okay, those Y values then come from the equation. So this point up here is going to be 0, 9. Okay, so this came from 0, 9, the left endpoint, that left corner of that rectangle. Okay, well the next one, okay, so again that was at 0, 9. Okay, the next one is at 1 something. Well, put in 1. So 1 squared is 1. 9 minus 1 is 8. So I'm going to be doing 1 times 8. Okay, and then the last one, again, I'm at the left endpoint, the left corner for this guy, and so it's going to be at 2 what? Well, 2 squared is 4. 9 minus 4 is 5. Okay, so 5. Okay, so this becomes 1 times 9 plus 1 times 8 plus 1 times 5, 22. Okay, so if that original thing was in centimeters, then our distance is approximately 22 centimeters. Okay, all right, I'm going to go through mid-RAM and, I'm sorry, right RAM and left RAM, right RAM and mid-RAM, sorry, it's early in the morning, and we'll go from there, and then we'll call it a day. So I have 2 more RAMs to do. Okay, so again, we're still on 9 minus t squared. What I want you to do is see what happens here. Okay, so velocity equals, so all we're going to do is, again, another approximation. And again, this is the parabola we're looking at. Sorry, it's supposed to go more like that. Okay, and again, so right RAM then is, again, we're going to still do 3 subintervals. Now understand that we could do 6 and it would be more accurate. There'd be less error sticking out. Okay, you can draw a picture and make sense out of that. Okay, so here I am on the right side of this rectangle. Okay, I'm going to go on the right side of this rectangle, and I'm going to go on the right side of the, yeah, I'm stuck. So that rectangle is going to be very easy to calculate the area of. Okay, so again, the same idea is true. Okay, so this again is right RAM, so right rectangular approximation method. I'm doing 3 subintervals. The more subintervals you do, the more accurate it is. Okay, and again, our goal is to approximate this area. And as we mentioned just a minute ago, this always creates a little bit of error. Okay, a lot of bit of error. Okay, because remember that this last one, the rectangle, is really just that line. Okay. All right, so here we go. We're going to do area, which is equal to distance. I should probably write it the other way around. Our goal is to approximate distance, which is equal to area, but we're approximating the area by doing 1 times something plus 1 times something plus 1 times something. Okay. Well, the something, in this case, this point is at 1 comma, put 1 in over here, 8. For the next rectangle, this point is at 2 something, and so it's going to be 2 squared is 4, so this is still 5. Okay, and then this last point is at 3 something. Well, 3 squared is 9, 9 minus 9 is 0, so this one is going to have a height of 0. Okay, so a little calculation here. So 8 plus 5 plus 0 is 13. Again, if that was in centimeters per second times seconds, we're at centimeters. Okay? All right, so where we're at, let me just kind of recap what happened here. This first approximation that we had was an overestimate at 22. This next approximation is an underestimate because I see area that I haven't covered. Okay. The last one is mid-RAM. Okay, MRAM. Okay, last one. Sorry, I know this is going a little long, but I need to get all 3 of these in here. So velocity, again, is 9 minus t squared. Okay, so again, we're going to do an approximation of this area, and sorry, the more I do this, the sloppier it gets because I'm trying to boogie. And again, I'm trying to go from 0 to 3, so I'm trying to approximate this area. Now, the difference is that we've been using the left end or the right end of a rectangle, the right edge. Well, what we're supposed to do is the y value that comes from the middle now. So depending on the curve, most of the time you're going to have a little bit in and a little bit out. Now, the cool thing about this is most of the time it follows the curve better. Okay, so again, here I am going up to this y value. But the bad part is, oftentimes the numbers are less fun to work with. Okay, so again, what's going on here is I'm actually going to use the x value 0.5 to calculate this point. Okay, so this point is going to be at 0.5 comma something. Okay, this point is going to be at 1.5 comma something, and this point is going to be at 2.5 comma, you guessed it, something. And those points have to come from this equation. Okay, in the interest of time, I'm not going to bore you with the typing. Okay, so through the magic of television, or YouTube as it is, those are your y values. Okay, so we're going to still set this up the same way. So again, distance is equal to the area. So that's going to be approximately, the width of each rectangle is still 1. Okay, so it still follows the same setup that we've been using, it's just the y values are now different. Okay, so let me fill those in. Okay, so there they are, and let's tally that up. So the area is actually 18.25, and again, if this is a distance, this is going to be in centimeters. Now, please understand that this is not the exact area. Now, do notice that this number that we just got, 1825, is in fact between 13 and 22, and is probably the better estimate of the three. Again, I do have some error going on. I have some underestimate and some overestimate. I have some underestimate and some overestimate. I have some underestimate and some overestimate. So there's still error, and the hope is that they kind of cancel each other out. Now, the magic thing will be to do lots of rectangles. And if I do enough rectangles, ultimately mid-RAM, left RAM, or right RAM really won't matter. And I know that's going to be amazing. I'm excited. All right, so that's it for us today, and thanks for watching. SanfordFlipMath out.